Well, as I say, it's been a couple of days since we did this, and I'm a little bit behind on these, and I hadn't realized that I had gone ahead and illustrated the divergence theorem with the same functions that we've been talking about. So, I bring you great tidings here. We can actually do this example, and it's really pretty straightforward. Okay, the divergence theorem simply says that the volume integral of the divergence of a function is equal to the surface integral of f dot vector ds, or f dot n dA, and this should be ds without the vector, and we could also say of f dot big N dA, where big N is your Rx cross Ry in this case. The cross product of your unit of your tangent vectors. Okay. Now, we do this, first of all, the volume integral, and we alluded to this earlier. We're just integrating over the usual inequalities that describe the unit sphere. And we're integrating the divergence function, which we calculated when we first saw our function f. Okay. So, right there is the integral. And again, there's nothing particularly difficult about this, except maybe integrating this cosine. You have some integration by parts. Now that integral is going to be equal to the integral of f dot n dA. Now previously we did the integral over the surface of the curl of f dot n, and that's different. Okay, f dot n is just how much of the function goes through the boundary. What's the component of f perpendicular to the boundary of your region, and through what area? Okay, in comparison with the area down in your xy plane. So that integral looks like this, and again we get our integral of sine of xy, which is unfortunate because that one's really kind of tricky. And I didn't put the limits on the integral here, but those would be the limits. And this is just an illustration of what the integral would look like for the divergence theorem. Now I'm not going to talk too much right now about the meaning of the divergence theorem. I've done that already to an extent, and I'll do a little bit more of that. And having said I'm not going to talk that much about it, I'll at least talk about this again. We've got whatever our region is, and this is a three-dimensional region, so we're maybe just looking at a cross-section of the three-dimensional region, and vector normal to the three-dimensional region at a point. Okay, and this could be our Rx cross Ry, or something else. You know, more in general, we have some other parameterization. We might not, our parameters might not be x and y. They could be theta and phi, whatever. We've looked at examples of that as well. And then you've got your function, your vector function f. So here's our vector function f. And we've got some increment of area down in our xy plane, for example, in this case, that gives us an increment of surface area, or if you want a normal surface area increment, ds equals n dA. So the component of f in the direction of n is just the projection of f onto the n vector, the scalar projection. So we just take whatever part of f is perpendicular to the surface, and then we're just going to multiply it by the area of the surface. Because remember that n dA, well, let's see, is n times ds, where the ds doesn't have an arrow. And the ds just means your area increment in whatever parameter plane you're integrating, in this case in the xy plane, multiplied by that magnitude of n over magnitude of n dot k. The or the square root of 1 plus fx squared plus fy squared depends again on your parameterization. Something that you multiply by your dA, and dA is not a vector. I shouldn't have written a vector there. Okay, your dA is multiplied by something to get your ds. Okay, that something again could be square root of 1 plus fx squared plus fy squared, which would work fine here. Or would it actually? That probably wouldn't. Or just the magnitude of big N. The magnitude of your Rx across Ry would also be a good multiplier. So, and you've seen it that way. You've seen it both ways. And the divergence is a little harder to describe. It's just whatever tends to push stuff out of this region. Okay, and why it's calculated as del dot f, well, that's a little more of a discussion. We've had it to some extent. We'll have a little bit more discussion of what that means. But again, an illustration of how you set up the integrals for a divergence theorem. And again, you get two integrals. You can pick which one. And it's kind of, a little tricky either way in this case.